right, so today is our very, very last day of gas laws. It's a short unit. We're going to look at something today called the Waals equation. You guys had this on the quiz, and I kind of gave you the answer previously. But ultimately, what the Waals equation is taking the ideal gas law and making it kind of really what it is. The ideal gas law assumes two things. It assumes that the molecules themselves are really, really, really tiny. They're just points in space. And it assumes that the molecules or atoms of gas aren't at all attracted to each other. Well, real gases actually do take up space and are attracted to each other. So the real perv nerd is this. You see how it resembles P, V, and RT? Okay? And what these extra things are in here, this thing and this thing, these are correction factors. These are factors that are put into PV equals nRT to make non-ideal gases more ideal. So you'll never have to do math with these. The only thing you'll ever have to do is a problem like at the bottom of your page where they're asking you to kind of explain which gas is more or less ideal using the equation as a place to start from. So let's look at your two correction factors. The first one I want to look at is the volume correction factor. This is the easiest one really to understand. Do you see how we're subtracting something off? Okay. What are we subtracting? Well, the N is actually number of moles, okay? And B and A in this equation are constants that you can find on tables, and everything in the whole wide world has its own constant. You never have to memorize them. Again, you're not going to have to do math with them. So that's where that stuff's coming from. But looking again at volume, we said ideal gases are teeny, and they themselves don't have any, volume. So if they do have volume, they're taking up more space technically, and technically they're making the overall volume of the container or of the gas itself larger, right? So what do we do to compensate for that? We subtract the correction factor. So that's why this B is actually subtracted. Okay? Does that make sense? All right. So let's look at the other correction factor. This is a correction factor for pressure. Ideal gases are not supposed to be attracted to each other. Well, they actually are. And since they have intermolecular forces and are attracted to each other, if they're attracted to each other, they're less apt to bounce off the sides of the container, right? So is that a smaller or a higher pressure? Smaller. So these real non-ideal gases actually have lower pressures because they're attracted to each other, and that keeps them from bouncing off the sides of the wall. So how do we compensate for that? We add to those pressures. And that's it. That's basically what the correction factors are for. So the way we would apply a problem like this is take a look, and I'm going to come back to this statement right here because it's a pretty important one. But what I want to do is apply this gas law. Explain in terms of the van der Waals equation why HCl is a much less ideal gas than hydrogen gas. So HCl versus H2. Which it's telling you this one's less ideal, but give me the two reasons why. And you'd have that van der Waals equation in front of you when you're answering this. Two reasons. The first one is the easy one, which is what? Larger. This has HCl is larger, so the B factor I forgot the M in compensates for the extra volume by subtracting, by subtraction. By subtracting from original volume. And again, these are going to be more of your multiple choice type questions, like which is more ideal, that kind of thing. You aren't often going to have to explain this in words. And then the other is the intermolecular force. Now I know we haven't covered this, so if I ever give you a problem right now, they're going to be simple like this. What type of molecule is HH? polar or nonpolar? This is nonpolar, okay? So it's going to have very little intermolecular attraction to other things. Versus HCl, we've got a dipole here, and you're going to learn about what this arrow means later. But this is a polar molecule, and they're going to be this simple. This is polar, okay? So that being polar means that has a higher intermolecular attraction. So HCl has a stronger intermolecular force causing a greater attraction. What does this do to pressure? This decreases. Oh, don't do this to me. This decreases, and I'm writing and nothing's showing up. Awesome. This decreases the pressure of the container, or in the container, of the gas in the container. Therefore, the correction factor is added to increase the pressure. This decreases pressure. Therefore, correction factor A is added to increase pressure. Y'all got that? Okay. I want to go back to the statement I mentioned down here that was really, really important. You're going to see this on SAT 2s, on AP exams, on ACTs. They always want to know, what conditions are gases most ideal? Gases are most ideal in terms of temperature and pressure. We want a situation where we have the gas molecules moving rapidly very far apart. So in terms of pressure and temperature, what would that be? Moving rapidly really far apart. High temp and low pressure. That's when they're most ideal, okay? And that's crucial. Here, this is just the opposite. So therefore, a gas deviates from being an ideal gas if the opposite is true. Not necessarily related directly to the van der Waals equation, but I just want you to hear that, because that's a common multiple choice type question that you'll run into. Okay. All right, last thing of the unit before we start our little quiz is mole fraction. For those of you using your iPads, go ahead and insert another page or blank page, because I'm going to do a little derivation. Those of you with paper, just turn your in-class problems over. You got the back that you can write on. Okay, so let me introduce you to the concept of mole fraction. Mole fraction is really simple. Mole simple, that's what I was going to write. Mole fraction. Mole fraction is indicated with a capital X, and you guys did this in solutions last year. You didn't do it in gas laws. You will be doing it again in solutions later. It's a very important concept. So say we want the mole fraction of gas A. What does that mean? It has to do with Dalton's law. Remember we said that Dalton's law, the total pressure is equal to the pressure of A plus all the gases in the room. Well, if we want to know the mole fraction of that gas, we would take the moles of gas A and divide it by total moles, meaning moles of A plus moles of B plus moles of C. Okay? This number is going to be a unitless number, and this number is going to be a decimal. You can write it out as a fraction, but you're going to be wrong in chemistry. Why? Why are fractions bad in chemistry? Yeah, the sig figs. They're exact numbers. They have an unlimited number of sig figs, and that's just not what we do. Okay? The AP graders are really, really picky on this mole fraction and partial pressure business of how they want to designate it. So please make that capital X. That is mole fraction. That's what it stands for. Okay? We can also find mole fraction using partial pressures, and this is the part that's kind of cool that I want to kind of derive for you. It's not hard, but If I were to take PV equals nRT and isolate the moles, what would my formula be? N equals R, no, it would be PV over RT. Okay, so I'm going to assume that I've got gas A, B, and C all in a container, okay? The container is going to be a rigid container. What does that mean? Volume is constant, correct? And then and I'm also going to keep a constant temperature. Because all the problems we're going to work at and we're dealing with mole fractions, they're going to be under these conditions, okay? Whenever we're looking at partial pressures. Like our room here has a constant volume, and we're going to be at a constant temperature. Keeping that in mind, I'm going to go ahead and just plug that into the above equation. So the mole fraction of A is equal to, instead of moles, I'm going to put PV over RT of A, okay, divided by the total moles of everything. So it's PV over RT of A plus PV over RT of B plus PV over RT of C. Okay, does everyone see what I just did? I took total moles, like this was really, I should have written moles of A plus B plus C there. And so I took the total moles. Now, keeping in mind our volume is constant and we're at a constant temperature, what happens to all of these? And what is R? Universal gas constant. What's going to happen? Those all can be divided out of every number. That's a number in every situation. And those all go, leaving us with the following. The mole fraction of A is equal to the partial pressure of A over the partial pressure of A plus B plus C. So another way to say that is mole fraction of A is equal to the partial pressure of A over the total pressure. Okay? That doesn't seem like it's a big deal, but here's where it's important. This is kind of going into something called Waals' law, which we'll cover more later. If you have a total pressure of the classroom, and I wanted to say, hey, what's the partial pressure of just nitrogen in this room? You could take the total pressure of the classroom, multiply it by the mole fraction of nitrogen, and get the partial pressure of nitrogen. And that's the same equation. I just rearranged it, okay? And I'm going to change this nitrogen to be any gas because we're really talking about any gas. So to find the actual partial pressure of any gas, you can take the total pressure of the room and multiply it by that particular gas's mole fraction, and you will actually get the partial pressure of that gas. So the equations that are important, all this mess I wrote up here, mole fraction and this one. These are the two equations. These and these are the same. I just rearranged it. Right here, they're the same. I just rearranged it, okay? All right, so let's apply it, and you're going to see how easy it is. It sounds a lot harder than it is, but by seeing it in action, you'll see how it works. These are the types of problems that you'll see this in. The mole fraction of nitrogen in air. So this is just the mole fraction of nitrogen is 0.7808. No units, right? Calculate the partial pressure of nitrogen. That's what we're looking for. When the atmospheric pressure is 760. What is that? P what? P total, exactly. There you go. So that's where we can use our little mole fraction situation. We know the total pressure is 760. Multiply that by the mole fraction of the gas in question. That will give us the P of that gas, and we're only looking at nitrogen. They're really sticklers about writing the correct symbols. You want the pressure, and then your subscript is what the partial pressure is of. So let's go ahead and calculate. Okay, so with 3 sig figs, it's 593. Because this is unitless again, we are going to say it's 593 torr. because that was the pressure of the original unit that was given to us in the atmospheric pressure. Another thing I want you guys to watch out for, I get students who, I don't know why, want to turn this into a percent. This is not a percent. And that's another thing that I've seen them not give credit for on the AP. Perfect mole fraction setup. The answer should be 0.78. Student report 78%. No points. Okay? Mole fraction is not a percent. And the final question, the partial pressure of oxygen, so we've got the partial pressure of O2, was observed to be 156 torrs. So we got a little bit of oxygen in this room, and that's its partial pressure. The atmospheric pressure, the total pressure of the room, is 743 torr. That's a pretty low pressure day. The question is, hey, what's the mole fraction of the oxygen? So how do we set it up? Well, we know total pressure times the what? Mole fraction of our oxygen will be giving us the, and the only thing you have to be aware of is make sure both of the pressures given in the problem are in the same unit. They don't have to be in, oh, and that's another thing I noticed on the quizzes. Whenever you guys were doing just the combined gas law or doing dimensional analysis with all the conditions changing, if you're going, if the pressure is increasing by this much and the temperature is increasing, a lot of you were converting to atmospheres. You don't have to do that unless you're using R. Okay? You don't need to change units. You do have to be in Kelvin, always. But with that whole pressure thing, you only need to be in atmospheres if you're using 0.082. All right, so what is our mole fraction of our oxygen? .210. Okay, that's it for the unit. Huzzah. That's what Nick King says a lot. Huzzah.